In this video, we are trying to understand how Stripe's document databases supported 99.999% of uptime with zero downtime data migrations. Just for your understanding, if you look over here, in 2023, Stripe processed nearly 1 trillion in total payments volume, all while maintaining an uptime of 99.999%. And as per the data, there are over 5,000 plus collections that are distributed over 2,000 plus database shards in their database. So what is Stripe's DocDB? Stripe's DocDB is nothing but an extension of MongoDB. So one common question that might come is why not only MongoDB? So back in 2011, MongoDB has certain limits. For the ones who don't know what MongoDB Atlas is, it's just a fully managed cloud database service for MongoDB that provides you infrastructure setup, scaling, backup, etc. So back in 2011, MongoDB didn't have anything like MongoDB Atlas. Also, MongoDB has certain vertical scaling limit, as you can see, to be of 4 TB over here. However, for providers like Azure, AWS, GCP, this number can be a bit high, like 10 TB, 15 TB, etc., depending on the instance that you taken. So, the ideal solution was to develop something that can help in horizontal scaling to overcome this vertical scaling limits of MongoDB compute and storage. And the solution is nothing but the data movement platform. We will discuss the design and the application of the movement platform a bit later in the part, but let's first understand what is the core idea of data movement platform. And before jumping into what's the architecture actually like, we will first understand how the database infrastructure in DocDB actually works. So, the core idea of data movement platform was to ensure that the online data migration between the shards are as less time taking as possible. So, for someone who is very new to the concept of shard is nothing but breaking up of a large database into smaller independent shards. If you look at the picture over here, you can see there is a large table over here that has 6 records. Herein, we are breaking this into small independent 3 separate databases, which you can see to be a shard, wherein the first 2 records are in one shard, the second 2 are in another, and the last 2 shards are in another shard. So from a very vague point of view, you can say shard actually helps in overcoming the single point of failure, as in there are several independent databases instead of one large database. Now comes how the database infrastructure actually works in Stripe. So the product applications at Stripe access the data in the database through a fleet of database proxy servers that were developed in Go. One question might be asked over here, or maybe you can have a question that why do we use this database proxy server? Well, as we discussed, in order to ensure that there's horizontal scaling, we are breaking up the large database into small independent shards, right? So as a developer, the code that I write don't know actually that which shard should I send the request to, right? And there should be someone who is telling me that, okay, as per this query, this is the shard that you need to trigger. So that's where the proxy server comes into picture. But again, if you see over here, how does even the proxy server know that, okay, as per this query, where to route the data? For that, we will be digging a bit dive into what is the proxy server doing and how does it understand that where should I route the query to? I mean, to which shard should I route the query to? Well, if you see something over here as the chunk metadata service, right? So when an application sends the query to the database proxy server, it basically parses the query, routes it to one or more shard, combines the result from those shards, and returns them back to the application. So, as a developer, I don't need to write any logic as to which shard I should forward the request, which we discussed earlier. And I also feel this architecture kind of helps in reducing the tight coupling. I mean, let's say an example, I am making a change on my routing criteria. I don't need to make a change in every part of the code that has a DB call, right? I only need to make a small change in the proxy server itself. Well, if you look at the picture over here, what chunk metadata service actually do is it's just a data structure that kind of stores key value mappings that, okay, for this chunk of data, this is the shard where it is present. So whenever a request comes from the Stripe API or any application in Stripe and it goes to database proxy server, it makes use of the information that's stored in chunk metadata service to find out which shard should I send the request to, because chunk meta service already has that key value mapping that, okay, this chunk of data is stored in this corresponding shard. However, if you look at the diagram over there, things aren't that pretty straightforward, because there is also something known as CDC, if you can look over here, right? We will come to this question of why use CDC when I have oplog, but before that, let's understand what is the use of CDC. If you look over here, I've given a pretty simple architecture or a more detailed outline of how CDC looks in action. Well, suppose the user writes certain queries and that actually updates your database. By update, I mean to say is that, let's take an example of a relational database, say MySQL, wherein we trigger a query, select star from users, wherein user ID equals to 1 to 3. So this is just a read query. I mean, even if the next query comes like select star from users where user ID equals to 4, 5, 6, this request actually doesn't depend on my previous query wherein select star from users wherein user ID equals to 1 to 3. But what if I ran a query that update first name equals to Rahul wherein user ID equals to 1 to 3. So the next time when I do select first name from users wherein user ID equals to 1 to 3, it actually depends on my first query. So there should be a way that I should know what are the queries that are executed on the database that might actually lead to update of my database. Now one question might come that why to store that? Well, let's take an example that when you are trying to update your database by any means, be it a delete mapping or it's an update mapping or anything. Let's say you are trying to update your database and at that point of time, your database fails. And you as a developer work on things and again spin up your database. But I need to make sure that when the database again spins up post recovery, it should know which are the operations that got failed so that it can again replicate those same things in my actual database, right? So that's one of the use case which oplog does. As you can see over here, the term oplog. So what oplog is? Oplog is nothing but a collection that's there in your MongoDB database that simply stores whatever operations are being executed that might possibly update your database. It's just the architecture of how MongoDB does things by using oplog. What does CDC does? CDC in simple term means change data capture pipeline. If you look at the image to your right, you can see what the pipeline actually is. In simple terms, whenever we are firing some operations on our database that might possibly update our database, our application will also trigger certain change events. And that change event is passed on to some streaming software, let's say Kafka in this case. And finally, the actual events are being stored in an object store, let's say S3. Now, one question might come over here that if MongoDB already provides a collection called oplog to store the queries that might possibly update our database, why are we again doing the same thing of storing it in an object store? Well, this is what I've mentioned over here, that why use CDC when have oplog. Well, keep this thing in mind how the architecture works. We will come to the question post we understand how the actual migration of data works from one shard to another. If we go a bit below, we can see how we design the data movement platform. So if you remember, I discussed earlier that the very core idea of data movement platform is to ensure that these online data migrations between the shards are as fast as possible, right? So whenever we're trying to design something like this, there should be some things that we keep in mind, like data consistency and completeness, availability, granularity and adaptability, and no performance impact to source shard. Well, these are very 4 broad points. You might break them up into very simple points as well. Coming to data consistency and completeness, by this I mean to say, whenever we are trying to migrate certain data between the source shard to the target shard, we need to ensure that the data being migrated across both the shards, let's say the source shard and the target shard, needs to be consistent, right? Coming to availability, well, as we have seen the statistics over there of 1 trillion payments and all, so we can understand that millions of businesses count on Stripe to accept their payments. And it's a 24 hours a day service, right? So the goal that needs to be kept in mind when we do the data migration is that ideally this phase of database migration should typically last just a few seconds so that the client knows that it's a very transparent manner. And the client doesn't need to understand that, okay, in the background, some migration is happening. The user experience should be the same. Coming to no performance impact to source shard, well, whenever we are migrating some database chunk from one shard to another, the source shard is still handling traffic, right? If you can see in this picture over here, my source shard is still handling traffic, even though the data is being migrated from the source shard to the target shard. So my goal is that even though the migration is happening, we should preserve the performance and the throughput of the source shard so that there is no adverse impact on the performance for the user queries that's coming in real time. So to address all of these requirements, the goal of the data movement platform was to make sure that these things go very fast. And this is the actual architecture of how data movement platform is built. You might see a few things over here like the op log, token number, and there's a question over here, the token number with each request why. Well, I'll make you understand things when we go with the flow. We'll first try to understand how each step goes over here, right? So the first step is step 1, known as the chunk migration registration. If I've seen over here something I've discussed earlier, that there is something called as the chunk metadata service, right? So as of now, what we know, chunk metadata service is just a data structure that stores key value mappings of what chunk is stored in which shard. Now, if you look at the architecture over here, in the first step of chunk migration registration, what we do is, we know that we are trying to migrate a database chunk from one source shard to target shard. But we as a user know this. The system also need to know that, okay, something like that is happening. So where do we register this intent? So we register the intent to migrate the database chunk from source shard to target shard in this we store this in the chunk metadata service. Another thing that we do in this step is we build index on the target shard. Now, if you need to know what index is, well, again, that's a very good topic to discuss about, but on very simple terms, if I want to give an example, let's take an example of the data over here, wherein you can see there is a table. Let's say it has columns like ID, user ID, name, age, and email. So take an example that your application fires up a lot of queries that depends on where user ID equals to anything. It can be 102, it can be 205, but it depends on the user ID a lot. So in the ideal case, if my database wants to get all the rows wherein user ID equals to 1 to 3, let's say select star from users wherein user ID equals to 1 to 3 or 102. So it needs to ideally scan all of the data and find out which all matches 102 and give me the exact count or data. But let's say if we know that, okay, our queries are a lot of dependent on this column of user ID, we can simply make an index on top of user ID. By index, what we do is, it's nothing but we simply make a data structure like a key value pair mapping, wherein we store our column in a very sorted manner. So if you look over here, herein the user ID is in a very random manner, like 102, 205, 301, 178. It's any random order. If you look at the index table, our column in which we need to perform the indexing, their data is stored in a very sorted manner. So right now, the advantage is, instead of looking at all of the entries in my table, I can simply look up to my index table based on the user ID parameter and find out, okay, where is the row that I should look up to? So it basically gives me the row pointer. Pointer means is nothing that stores the address of that corresponding entry in the disk, and I can get the data from there. So what's the advantage over here? So ideally in this case, in the very naive case, we are trying to iterate all the possible data. So you can take it off as a big of n complexity, right? But in this case, since the data is already sorted, instead of looking for all the entries in my user ID, I can simply perform a binary search and find out that, okay, 102 is here and this is the corresponding row entry. So the timing can be optimized from big O of n to big O of log n because of the binary search. Again, this is a very vague idea of how indexing can help. In the very low level architecture, it's implemented using something known as the B trees or the B plus trees. So coming to where we left off, in the chunk migration registration, the first step of migrating a data from the source shard to the target shard, within it, what we do, we register the intent to migrate the database chunk from the source shard to the target shard so that my data movement platform knows what is being migrated. And we store this in the chunk metadata service. And what we do secondly, we build an index on the target shard. Now, one question might arise over here. Do we migrate data and then index, or should we already index and then migrate the data? So this can be depending on what kind of architecture you follow. But if I talk about how Stripe does it, it already built the indexes on the target shard and then migrate the data. Coming to why, we will cover it in the second step. That is bulk data import. This step, as the name suggests, we simply migrate our actual data from the source shard to the target shard. How do we do that? We take a snapshot T of the data present in the source shard and simply migrate the data from the source to the target shard using an internal service that Stripe has built. However, while trying to do this, Stripe noticed that, well, the data that's stored in one shard is not like simply 3 to 4 data or 5 data. There are terabytes of data. So whenever, ideally, when you are trying to migrate some large amount of data from one shard to target shard, Stripe faced some throughput issue since it's a it's a very large data, right? So they tried to make certain optimizations to their engine and stuff to solve it, but ideally none came of much help. So if you look at the second point over here, what's the way to optimize our throughput, right? So well, if you have noticed somewhere that our index table stores the specific column in a very sorted manner. Like the user ID over here is stored in a very sorted manner, like 102, 123, 154 and goes on till 450. So what if instead of sorting, if I migrate my data from the source shard to the target shard, the B tree that applies those index at each step needs to make a lot of changes to its structure because the data is coming in any random manner. So if it's coming in any random manner and I need to make my data store in a sorted way, at every step when the data comes, I need to make change to my B tree. However, one thing that Stripe noticed, or rather it's very, very trivial to understand here, that instead of migrating the data from the source shard to the target shard in any random manner, if we migrate the data in the sorted manner, then, when I mean to say in a sorted manner, I mean to say that if I migrate the data in a sorted manner based on my column that I try to index, like in this case, if I pass the data, which is already sorted in terms of user ID, so then at each step, B tree doesn't need to make much changes or make much updates to its structure. Because the ultimate goal of B tree is to make sure that the data is sorted according to its index. But if we are already passing the data in a sorted manner based on the index, then the B tree doesn't need to make much change. And with this, Stripe gained a performance improvement of 10x, which you can see over here. Coming to the step 3, it's asynchronous replication. Well, you might have noticed something over here that I've mentioned. Why should we use CDC when we have oplog, right? Well, if suppose there are a migration going on from the source shard to the target shard, as I've mentioned, for a time t. So the time post t, there can be a case that certain writes have already happened on the source shard. Now a question might come why, but I've already mentioned that the source shard is still handling traffic when migration is going on. So post time t, there can be a cases wherein some updates are already made to this source shard. So in the ideal scenario, we need to replicate those same thing to my target shard. So what I do over here, instead of relying on my oplog, if you have seen the pipeline over here, wherein the oplogs are ultimately stored to an object store through the Kafka streaming software, right? So in this third step of asynchronous replication, my target shard makes use of those oplogs written in object store and makes those actual same changes in my target shard instead of using oplog. And now coming to the answer of the question that why are we using that object store via the CDC pipeline and not oplog? Well, during this time, my source shard is handling real-time traffic, right? So if my target shard is constantly trying to access this oplog collection in the source shard, it might lead to some performance issue. Or if not performance issue, in the ideal scenario, I want all of the throughput and the performance of the source shard should be applicable or available to the real-time users. So in this case, if my target shard hits queries to my source shard to fetch the oplog, it simply means that a certain throughput of the source shard is being shared with the target shard. And as in, I can say my users are not being able to make full use of the source shard. That's the reason instead of having a tight coupling or making direct queries to the source shard, I am simply accessing those oplogs via the object stores, let's say S3. And this in turn also helps in reducing the tight coupling between the source shard and the target shard. Coming to the second point, as this replication is actually a bidirectional replication, but you might say, okay, Hindol, if already the source shard is handling traffic and we are migrating the data to the target shard, what's the need of bidirectional replication? Well, let's say post the migration as all is done, there are some issues to the target shard and we might need to again reroute our traffic to the source shard. So again, we need to make sure that during that time, whatever writes happened on the target shard needs to be migrated to the source shard as well. So that's why Stripe has something called bidirectional replication, just to make sure in case if the target shard fails and we direct our traffic to the source shard, there is also a way to migrate or update the same things that happened in target shard during that meantime to the source shard. And the last point for this, okay, but what if cyclic replication happens? That, okay, the source shard has made some changes to the target shard via the replication, and then what if the target shard has been accepting traffic and it fails? So then we make the same changes that happened in the target shard to the source shard. But what if this occurs in a cyclic manner? Like, let's put things simply. Suppose you update a place from 1 to 3 to 4, 5, 6 in the source shard. So now my target shard uses the oplog and makes the same change in 4, 5, 6. What if the replication engine understands that, okay, a new write has happened and issues another same thing from the target shard to the source shard, that change 456 to 456. The source shard already knows that this change has happened. So why should I do it? Only the target shard should do it, right? So that's why Stripe uses something known as the service tags or replication service tags. So what's happened in this case? Whenever the replication engine migrates some writes from the source shard to the target shard, it associates a service tag to it, so that once that change has occurred to the target shard, it should not again trigger that same change to the source shard, because right now we have that service tag to validate that, okay, this replication has already happened. Coming to the fourth step of correctness check. Well, this is just a point in time snapshot check between the source shard and the target shard, just to make sure things are pretty fine. So what do we do in this step? We simply take a point in time snapshot of the source shard, take a point in time snapshot of the target shard, and just do a compare that, okay, if both are consistent in the shards or not. Coming to the most important step of traffic switching. Well, you might have seen in the picture over here that I've added a line, token number with each request y, and I've also added a line that the source shard, apart from oplog, also has a collection called the token number. So right now, I know that my migration of the data has happened from the source shard to the target shard. Now there is ideally no need for the source shard. I can directly handle or route my traffic via the target shard. How does this happen? So proxy servers, whenever they send a request to the source shard, they attach a specific token number to the request. And the source shard in their token number collection also has a specific token number stored to it. So there is a custom patching in the database that enforces that the request coming from the proxy server, the token number present in it must be greater than the token number that's present in the collection of the source shard. How does this help? So imagine in this scenario, when I want that all my traffic should move to target shard and not to source shard, what will I do? I'll simply bump up the version number of the token in my source shard. So whatever proxy server queries are coming to the source shard will simply be rejected. Be it a read, be it a write, anything. Because the token number that present in the source shard is now greater than the token number that's coming from the proxy server. So ideally, all the read or the write requests that are coming to the source shard are rejected. And now at this point of time, I can simply update my chunk metadata service that, okay, for this chunk of data, don't point to the source shard, but point to the target shard. So right now, all of my traffic that the proxy server actually directs to is my target shard and not my source shard. Also, I missed one point that whenever we're updating the chunk metadata service, that, okay, this chunk is pointing to my target shard, we also add that corresponding token number in the target shard as well. So right now, the target shard has the corresponding token number or the version number that's actually less than what the proxy server is sending. So now, whatever proxy servers is routing to is actually pointing to the target shard and not to my source shard. Now, a common scenario might come that what if some stale writes are already there that are being already pointed to source shard before even making that change in chunk metadata service? Well, again, that's what I mean. Even if there are stale reads or writes coming in from the chunk metadata service before its update, well, the source shard token number is already bumped up before making that change. So even though there are some stale reads or writes coming in, the request that comes from the proxy server has a version number that's higher than what stored in the, that's less than what's stored in the source shard. So ideally, even though if some stale read or writes are coming into the source shard, it's simply rejected. And then when post the chunk metadata service is fully updated, I know that whatever requests are coming with their token number is actually higher than what's there in the target shard. So right now, whatever traffic that comes via the Stripe applications are now migrated to the target shard in place of the source shard. And that's how this step actually completes, right, this traffic switch, which I have written over here also as the rerouting traffic how, remember the token number, and update the chunk metadata service. Coming to the last step of how the chunk migration deregistration works. Well, if I've seen in step 1, we are registering the intent. By registering intent, we simply mean that making an entry in the chunk metadata service that something is going to happen. I mean, some migration is going to happen from the source shard to the target shard. And similarly, in the chunk migration deregistration, we simply mark that entry in the chunk metadata service as completed. That's it. And now, whatever traffic is coming in to my proxy server is now fully pointed to the target shard. And that's how this entire migration step is now completed. Well, you might have seen there's one point I've added over here, granularity and adaptability. Why didn't I cover it earlier is, by granularity and adaptability, we mean to say that data movement platform ensures there shouldn't be any limit on the number of concurrent migrations going on. And there should also be no limit on the number of source shards that are taking part in a migration. So this is yet another consideration that's being taken in mind while we design the data movement platform. And what's the architecture, as I've discussed over here, and how the actual migration goes on. Well, this is one of a beautiful architecture that I went through, and I won't say that this architecture is something that you can exactly replicate on your system, because it's depending on the architecture you are building or what's your use case. But this is one of the way of how you can build databases with high availability and low downtime or zero downtime data migrations. Well, that's it for the video. Thank you for your patience.